Problem number 1, world population. Here's the data. Get it into your calculator. It should look like this. Make sure you get everything in right. Double check your entry. Once you're done, you can stop the recording or whatever and then continue once you have your data in. Once you have it in, do a scatter plot. So second y equal. Make sure you turn it on. It should be on L1 and L2. Zoom 9. Okay, now you can see already the data is curved. Okay, but maybe you think, oh, maybe it's straight enough. Who knows? Are you hoping for the best or whatever? Make sure that you have hit second catalog and then the inverse key and then down 9 to turn on diagnostic. And on. Okay, that's second, 0 key, and then hit the inverse key to put you in the D's, and then arrow down to diagnostic, enter, and then enter again. Okay, diagnostic is turned on. And okay, so let's do a stat calc 8 on L1 and L2, which are the defaults. And now we've created residuals. So the next thing we want to do is look at the residuals. Second y equals, we don't know if that's the line of best fit that goes with our scatter plot. Let's look at the residuals. And I arrow down to L2 and I hit second and stat to get into the lists. I'm in the list menu, and number 7 is res ID, hit enter. Okay, zoom 9. And you can see the residuals have a big curve in them, so this is not a linear association, so we can't use this model that we just created. I'm going to clear it all out. Okay, so the residuals really show the curves. What are we going to do? Well, the y-coordinates must be re-expressed. Since this is population growth according to the table above, we should use logs. So we'll use the logs. Now, let me go through that. Okay, so I'm going to do stat and then edit, and I'm going to go to L3. Now, when I say we're going to use logs, that is, if you look at the L1 data, this is the explanatory data, the x coordinates or whatever, they're in fairly regular increments, 0, 5, 10, 15, 20, 25, 30, and so on. It's the y data that is increasing at a non-regular rate, at some kind of exponential rate or something else that's causing the data to be curved, which is why we need to re-express it. So we're going to try converting the y data to logarithms and see if we can get a straight linear regression. Then we can do analysis on that. Now we're going to do a whole heck of a lot of analysis on it. We'll do that later on in the course. But you need to know how to do it now. All right, so I'm going to go, here I am in L2. I'm going to go to the top of L3. So if you're down here or whatever, go up to the top, and you're going to hit the key that says log, and we're going to hit second and 3, and then close parenthesis. Now what we're going to do, well, we're going to put in L3. What did I do wrong? I don't know what the heck I did wrong. Let me try it again. Stat. Okay, top of L3. Log. Oh, I put in L3. Second, and then 2. We're going to put in L2. I put in L3 before. Okay, whatever. All right. Now what's in L3 is the exponent that 10 must be raised to get 2519. So we got 3.4012. If I were to leave this, and I would take 10 and raise it up to the 3.4012 and hit enter, I get, well, effectively 2519. I'd need more decimal places to get back to 2519. But I think you get the drift. Okay, so what's in in L3 is the exponent that 10 must be raised to in order to get 2519. Well, why does this help? Because exponents grow much less quickly and rapidly than do their product, the products that are created when the base is raised to that power. Okay, you can look at these. Here's 2519. Look at the difference between 2519 and 2755 versus the difference between 3.4012, the exponent that 10 must be raised to get 2519, and the exponent that 10 must be raised to give 2755. You can see the difference between them is a few hundredths. Okay, since the differences are so much smaller for the exponents, it's possible that we'll get a straighter association. Okay, that's what we're hoping for. Okay, all right. So let's make the scatter plot. Okay, we've got L1 and L3. So let's go to second and y equals, and we'll go in here, and we'll go down, and we'll make a scatter plot. Second, I mean, it might be the scatter plot's just ridiculous, like it's got a big fat curve in it. It means we can't use it. We won't even bother doing linear regression. Okay, so I got L1 and L3, and I do zoom 9. Okay, so now, I don't know. I mean, it looks curved, okay? Maybe it's okay. It's hard to tell. The way we can really tell whether or not we have created a linear association by re-expressing is by doing lin-reg and then looking at the residuals. Okay, so we're going to do stat calc 8, and we'll put in L1, comma, L3. And we hit enter. Okay, and now we got some stuff here. Now let's look at the residuals. We created the residuals, so we'll do second y equals, and we'll go into this guy here, and we'll go second and stat for list, and then 7 for res ID, enter, and then zoom 9. Let's see what we got. Well, we pretty much have the same dipsy doodle that we had before. Okay, it goes up and then it goes down again. So we still don't have a linear association. So we got to try something else. Okay, so scatter plot looks identical, but the residuals, I got this all in here. Okay, like identical. So we're going to try the square root of the y coordinates. Okay, now in this example I put it in L4. I guess I'll put it in L4 here, but you don't have to. Since L3 is no good, okay, we're not going to use L3. You could put it in L3. It doesn't really matter. Okay, but since I have it in my example, since I already have it here in L3, I'll put it in L4. So here's how I did it. L4 equals square root of L2. So I'll do it here. So I'll go to stat and edit, and I'll go over to L4, arrow up to the top. Like I said, you could do this in L3. And I'll do second square root of L2. Remember, L2 is the original data, so we're not going to do it on L3. We're going to do it on the original data, the original Y data, the consequential data. So I hit enter. Okay, so here's the square roots of these guys. Now also notice the square roots grow more slowly than do the numbers in L2. Okay, we have a similar effect that we got from logs. Okay, not as dramatic. Okay, but still, look, we increased by 2, increased by 2, 2. I mean, it looks a little more regular. Okay, all right. So it looks promising what we see so far in L4, and that there does seem to be a possible steady rate of growth. All right, so let's do a scatter plot. So we're going to go into our plot 1. You can use other plots if you want. I find it simpler just use the same plot over and over again. I don't get them all mixed up. So now I'm going to use, instead of L3, I'm going to use L1 and L4. Notice we've always been using the same x coordinates, the same inputs. Okay, so I hit zoom 9. These guys look really straight. Straight arrow. Okay, all right, they look straighter than what we've had before. You can compare them. You can see I kept all the pictures here. Okay. All right, you can see the other scatter plots. All right, so it looks a little straighter. Okay. All right, so we're going to, let's clear this screen before we got a lot of stuff here. All right, so I'm going to do stat calc 8 only. What did I forget to do? Stat, I forgot to do it on L1 and L4. Stat calc 8. Second 1, comma, second 4. If you're using L3, then obviously you'd put in L3. Okay, now that's what I wanted to do. So now let's look at the residuals. So I'll do second and y equals. Now each time that I've run the linear regression, I've created a new set of residuals. So the residual, a res ID holds the residuals created by the most recent time that you ran linear regression. So I don't know if there's not like there's multiple residuals files. There's simply one. It holds the most recent batch of residuals. So I do second and list and 7 for res ID, and I hit enter in Zoom 9. Okay, the residuals look kind of lousy, but they look better than what we had. Okay, and this is as good as it's going to get. And that's how it is with re-expression. It's not always, you're not always going to get something really great. So here's my residuals, they look better. So let me put my stuff back on the screen here. So here's my model, 49 point, I've rounded up to 49 point, actually 49.63 is probably more correct, 49.631. I could fix that, 63 here. Okay. All right, plus and then 5.66 times the year. And that's a year since 1950. You know, that's something I've really forgot to, you know, I'm sorry I didn't mention that. After all this time, I'm called 1950 year zero. You probably figured that out already. Anyway, so here's the model. You have to write it like this. Square root of estimated population equals 49.63 plus 5.66 times the year. You remember this from part 2. You don't put in y and x. Okay, we put in the contextual variable name that refers that we're using in the equation. Okay, that we're attempting to describe a relationship between. Okay, prediction for 2005. So we plug in. Remember, 1950 is the first year, so we plug in 55. So this is the estimated square root, 80.77. So we square that number, and we get 6,523.8 million people, or 6 billion, about 6.5 billion people in 2005, which I don't know how accurate that was. I know we're up to 7 billion now. Okay, now I want to show you this thing. I showed you this in class. I'm going to go over this again. And namely, okay, suppose you had to, it was pretty easy to find 55. We just plug it into these numbers or whatever. But the calculator's done a lot of work for you so far. How can you get the calculator to help you? Let's suppose you had to generate estimations for 2004, 2003, 2002, 2001, etc. Okay, using your model, what would you do? Well, first thing you want to do is you want to go to VARS and take the equation that you just produced. Go to VARS 5 for statistics, arrow over to EQ, and there's RegEQ. That's the equation that you just created. Just like LinReg holds the most latest residuals from the last time. I'm sorry, Res ID holds the latest residuals. RegEQ holds the latest regression equation. Y equals A, so it's going to be Y equals, you're going to see here, we'll hit enter. And there it is. There's A plus, and then B times X. Okay, that's nice. Now that's the square root of the estimated. This Y1 is the square root. That Y1 stands for the square root of the estimated population. That's what Y1 is here in this equation. So if we take Y1 and we square it, we'll have our actual estimated population. So what I'm going to do here, I'm going to go to VARS and over to YVARS. And function for Y1, hit enter. And then if I square this, I now have the actual estimated amounts. So I can then go to second and then into the table. And here I can compare these to, here, let's go. Here's the actual amount. Okay. So Here's the actual amounts for year 0. Well, the predicted is 2463 and then 25. You can see they're off. Okay. Oh, here's year 5. I'm sorry. Year 5 is 2751. Well, that's year 5 is pretty close. Okay. How about year 10? Year 10. Okay. Year 10 is 3020. That's year 3056. So this one's a little too high. And so on. Now you wanted to find year 55, you could just arrow down. It only can take very long. 20, 30, 40. Okay, 1, 2, 3, 4. Okay, and there's your 55, 6518.7. Okay, and that was what our answer was, when we plugged it into the calculator. Okay, so the calculator can do a lot for you in terms of if you have to do a lot of calculations. Okay, so that's it for the first problem.